Okay, so thank you for coming back. I thought that was the first hour. I said, okay, I'm done with this class. So I want to also add something that I didn't mention before. If there is a question that you have, or if there is something that you would like to ask, me, just send me an email today, to whatever, and I'll make sure to add your question, the answer, and some little bit of discussion tomorrow also, okay? So I don't want it just to be a section in which I give you some information. I understand that it's not complete, it cannot be complete, and I'm sure you have some questions. So feel free to send me an email. You will find the email if you want. I didn't give the email. So, but it's on the website also. But you will send me an email and I'll make sure that the question are added to the discussion, okay? So, well, it should be on the Combustion school, but if it's not, if you do my last name, University of Michigan, you will find me, okay? So make sure to do that. I'll make time to find an answer and discuss this with you. So let's do that. Okay, so now I need to dive a little bit into the quantum chemistry, and I'll promise I'll try to be not go into many details, but I want to tell you a little bit why people, when you go and say, oh, I have done these DFT calculations, what do they compute? Why they use that? Okay, so the information that we can get. So we look at Faraday's inside. We talk about this. Historically, there was a wax, there were gases. Soot precursors, I show you some of the experiments. You know, people measure stuff, they see pHs. But the question is, how do molecules form? You know, why those small hydrocarbons transform into more complex structures that eventually becomes nanoparticle? And what are the pathways of this reaction? Why some fuel forms more soot than others, okay? And so at this point, in order to answer those questions, and again, I always am interested in those questions, why? And then I find the tool that I can use it. So in this case, I'm going to look at a little bit of the quantum chemistry. So first of all, just to have one slide that relates to normal life. This is a neon sign, right? That you have seen a lot of this. Do you know how this works? Some of you? I'll tell you in a moment in this presentation, okay? So try to connect with the real life a little bit. So let me go back here. So this is I already showed you. And again, I am going to look right now for this combustion chemistry, we're looking at the gas phase. So those, you start from fuel, you break down, and now you're looking at the formation of those species. Why this has happened and what are the main drivers? So the bridge is, so the goal is to bridge what are some of the macroscopic observations. For example, people go sample the flame and find compound that has, let's say, let's say a pyrene, maybe as an aliphatic chain, maybe as oxygen, maybe as 5-member rings. Why? And so can we bridge those macroscopic observation to the quantum level of those reactions? And so let's talk for a little bit about quantum chemistry, and then this will also set the stage for my Monte Carlo and MD in the next things. And so the first part, that this next hour or 45 minutes, we're going to talk about a little bit of an introduction to quantum chemistry, and then we'll conclude today with the other section, applied quantum chemistry to combustion, why people use it, what insights they can get. So first of all, why quantum chemistry? People have worked for many years with the classical chemistry, but there were very many limitations, especially the fact that the atoms were rigid balls, and so there was no description of electrons, for example. And when you talk about bond making, bond breaking, you need to have some electrons. But what really, so the quantum chemistry provided these fundamental rules by which atoms can play. So we are doing it at a level that is much smaller than what you have seen until now. And so can describe electrons, predict some of the property, elucidate mechanism rates, and spectroscopic properties. So if you have an experiment and you have a spectra and you say, okay, I want to model this spectra, then go back to quantum chemistry. Those are some of the properties, the characteristics that you can compute once you have quantum chemistry. So it's basically the language of the electrons, and we are going to look at bond making and the molecular transformations. So I have here this, and this is the, I think it's in the note, but this is the ultraviolet catastrophe that happens when you try to look at the radiation body, and when you move down to small wavelength, classical chemistry, the ultraviolet catastrophe, sorry, website, will predict that the energy goes up, but in reality, what you see is that it goes down in this region. And so classical chemistry was not able to predict that. So that was like a turning point in which people decided that maybe we needed something else for that. And so quantum chemistry can, in this simulation that I'm going to show you, can describe the position, the energy of the electrons within a molecule. Okay? And that means also when you have the bond or when you break the bond. Predicts molecular structure, the stability, the energy, and can help with the reaction mechanism. Remember, our goal is to go from fuel, for example, all the way to those pHs. So quantum chemistry is really the way to do this here. And then rates, how fast you convert. So, for example, when you have, you're thinking of designing a new fuel, or you want to see that, you know, maybe I'm mixing this fuel with something else. Rates become important. So if your goal, for example, is to produce a certain amount of pyrene, I'm just giving you an example, then the pathways are going to be affected, but also the rate. So quantum chemistry can help you with the rates, how fast this is going, and that will tell you which one is maybe the most important pathways or the relative importance of different pathways. So how fast those reactions occur, and they also, are of interest for the spectroscopic properties. So they are fingerprints and can detect species. So what I'm showing you is an example in which we work with the experimental people. They had the spectra, okay? And they had no idea what compounds was inside, okay? They didn't measure that. So those kind of molecular study can tell you that. They can say maybe in this condition, this is the probability that you develop this product, okay? And so the spectra can be just a way to also, with this quantum chemistry, to fingerprint what's inside, for example, a flame, okay? So quantum chemistry of pyrene, with quantum chemistry you produce a spectra of pyrene. Then you compare this computed spectra with experimental spectra, and then you can assess if those are the species that are inside, okay? So, and so again, this is just an iteration that really gives the fundamental rules by which atoms in a flame play their part. So, before I keep going forward, some people use interchangeably quantum mechanics and quantum chemistry, and I just want to give you a clarification on the definition. So quantum mechanics is the fundamental theory of those scale, atomistic scale, okay? Describe the particles, the electrons as the waves, okay? And the principle are quantization of energy, the wave particle, and the uncertainty. Quantum chemistry is the application of quantum mechanics to chemical problems. So electronic structure, bonding, reactivity, those are all applications of this theory. So what we are going to do is to look a little bit at the quantum mechanics equation, so Schrödinger equation briefly, and then apply to chemical problems, okay? And so QC is a QM applied to chemistry, if you want. And so physics and engineering could be another thing if you want to. Okay, so quantum mechanics. What happened? Well, this is just summarizing the main points, and then I will go into some other details. Classical physics failed to reproduce some of the experimental evidence, and the black body radiation, photoelectric effect, those are all things that classical physics was not able to express. Planck in 1900 solved this black body problem with a kind of a revolutionary idea for sure, that energy is not continuous but discrete. So energy is quantized in those packets. This is the famous equation, so the energy quantization, E is equal H, that is the Planck's constant, and then nu is the frequency that you have. And again, those quantums are those smallest units of energy that you can have. So if you have, so I can do it this, okay. Imagine that your coffee, you know, you leave the cup of coffee on the table, and so now you're looking over time how the temperature goes down, okay? And so usually what would you expect is something that looks like this, right? Over time, that goes basically to the equilibrium of the temperature that you have in the room. Your coffee is getting cold. But imagine now that only certain temperatures are possible. So what's happening in reality is something that looks like this, the blue one, the staircase, that water. And what this basically means is related to the energy that is inside the coffee. So the coffee will go from this high energy level all the way down, but of course it will do this in steps. It's not a continuous like the red, but it's more like the blue. So this is the overall idea if you want, but at the macroscopic level, when you have big things, there are a lot of atoms included. And so what you see here, your coffee getting cold, they will look like this, you know. So you still have this staircase, but you're looking at a different scale, macroscopic, and then it will look eventually like a line. But if you dive into the microscopic world, and what we are dealing now with atoms and molecules, then energy is like this, okay? It's a staircase, and you have this energy levels that you need to take into account. So the key issue is the relative spacing of energy versus the total amount of energy. So this is important. If you're here and you want to jump down, for example, how can you jump down? What kind of energy are you releasing? So 2 points, the total amount of energy, but also the spacing between those levels. Okay, so how easy is to go down in this state. And so here we have Max Planck. This is in 1900, and German physicist, and discovery of energy quanta won him the Nobel Prize in 1918. But basically what he says, the energy is quantized and Planck suggested that radiated energy can only come in quantized packets outside UV. So you have the energy is equal Planck's constant multiplied nu, okay? Remember, you need this, you need to understand the energy of the molecules and what they can do, those molecules, especially in a flame environment. So that's the reason why we're going this way right now. And then here is the 1D, so the simple one, 1D, the Schrödinger equation, in which, so this is Erwin Schrödinger, similar period, he also a Nobel Prize, okay, from Austria. And his results are the fundamental result in quantum theory. So what does this tell you? Basically, it's a complicated expression. I don't need you to remember, of course. But the idea is that if you combine this kind of a function, this is a psi function, you take the second derivative, you multiply here for h bar, that is related to the constant Planck, and divided by the mass. And then you add some potential energy, so this is the kinetic energy, this is the potential energy, then you get some allowed total energy in your system, okay? Complicated, but there are ways to solve that with different software, okay? So you don't need to worry about the math, but you need to worry if you want about the meaning of all those things. So solving the equation for a given potential V, and a set of boundary condition, like a molecule in the box, yields a set of wave function and energy that are said to be allowed. So N is basically specified state. Okay, so I'm looking for ways to understand the energy of the structures here, and so with the N. So again, this is the kinetic energy that I'm looking here. This is the potential energy, and this is the allowed state. And with a psi that you see, function of x is a 1D that I show you, so it's a distance basically, is the probability that the system is located between, in this case, x and x plus dx, okay? So we need to know the likelihood that you are making a bond, that you are breaking a bond, right? you need to know where the electrons are. You have a probability for that. And so what this is going to give you is basically the allowed energy levels for the system. So if you have a benzene in this high temperature, those are the allowed states, okay? So, but before we look at some of the results with this, I want to tell you a little bit about, given a molecule, what are the allowed energy states that you can have? So if I put my acetylene in 2000 Kelvin, where does the energy go? So the first thing is that this is, well, some of you might know, this is the Schrödinger cat, right? And it's basically, it's a famous way for Schrödinger to describe this equation. And the thought process is that if you have a cat in a box and then there is a vial that breaks, eventually it can kill the cat. So the question is the cat alive or dead? But the point is that you don't know until you open the box. So, and is neither dead or alive in this point, is in a superposition of states, okay? So this is a different way to look at reality based on quantum chemistry. But part of those equations and again, this approach. So what happens if you have an atom? I have one atom. I want to know, I'm placing in a high temperature, for example, what kind of energy can it have? Well, the electrons have electronic energy. Changes in the kinetic and potential energy of one or more electrons associated with the nucleus, also this is that. And then there is a nuclear motion, so the translational energy. The atom can move in space, okay? So one atom is relatively simple for those things. What about translational energy? So if you have 1D motion along the x dimension of the particle, this is the type of expression. Now remember, I need to go back to the Schrödinger equation. So I need all those information about the state and the type of energy. So what you see here for 1D, again, don't worry too much about the equation. The idea is that we need this type of information to get to my reaction pathway. So if the molecule is in 1D, you have just one atom moving, this is the type of translational energy. If it's in 3D, so it's a little bit more complicated, then the expression takes into account the different directions, okay? And now you have a lot more of those states that are allowed. This is just translational energy for an atom. What happens now if I have a molecule? Well, I still have the electronic energy, but then I have more contribution, if you want, to the kinetic energy. Translational energy is the same. You know, you have one atom or you have two atoms, still the kinetic energy is the same. What you have in addition is the rotational energy, so Schrödinger equation, vibrational energy, so the nuclei can move relative to one another. And what we need is solve the Schrödinger equation for those energy levels. So if you have a diatomic molecules, now what are the rotational levels? So the first one is this. So let's think about, those are molecules here that you have. This is the distance, this is the center of mass, of course, I mean, this point here. And so the moment of inertia for the system, this I, is basically a function of the mass multiplied the square of the distance from the center of mass, plus the second mass times the distance. The Schrödinger equation for the rigid provides some energy level. So the energy level are, again, the h bar. And then you have this I related to moment of inertia and j. You don't need to worry. If you look at Gaussian view as a package, it's going to compute all those terms for you. Okay? So what it's doing is solving the equation and give you those information for the electric state, for those allowed states here. But I want you to give you a feeling of what, if someone ran a Gaussian simulation, what does that mean? Why they're doing this? And so this is interesting. So this is rotational energy. So you can be in this state, E0, you can go E1. And if you move a one state, remember they are integers, so you can only have a quantized energy. So then J equals 1 brings you here, and then you keep going. Now, for rotational energy, as you move up in energy, those bands, they are wider. So think about this. Why I'm wasting so much time on these things, and I know that I don't want to lose you with all this math. If you want to jump from this state to this state, you need a certain type of energy. If you want to do one more jump, you need way more energy here, okay? So it's not continuous, but there is a jump. The system needs to have enough energy to go up. The degenerance is fine. Okay. Then I have vibrational energy level. So you have, in this case, an harmonic oscillator. So you have, again, an atom, two molecules here. There is a distance. And solving the Schrödinger equation for the for his harmonic oscillator give you something that looks like this. So you have nu again, and then you have h. And now, I don't know, this is not my fault. This is the same symbol, but this is the frequency. This is the allowed states that you have. Okay, so 0, 1, 2. Let's see, go back here. Okay. So rotational case, the energy go up with the J, right? So actually J times J in that case. This one, the energy goes up also with, in a different trend, but it's the same, it goes up. And so the energy levels that you see here, this is a vibrational things, are equally spaced. Okay? So again, a lot of information, but let's say that you want an excited state. You want to move the energy of your electrons. Well, if you want to vibrationally activate them, maybe this is the amount of energy and they are equally spaced. If you want to do rotationally this, and of course then the energy is different. I show you the gap is much bigger. So those are all ways in which you, for example, give energy to a molecule, and that's the ways of storing this kind of energy or using it. And so this is the lowest state is not zero. This is interesting here, and is 0 point energy. How many times, maybe if you run a Gaussian simulation, there is a 0 point energy that you need to compute, or those are some of the questions that people ask also when you use these tools. So the 0 point energy is basically the difference is here. Okay, and so you need to include that in your energy level. That's the reason why people sometimes compute this 0 point energy. Now, in this same principle, there is the bond dissociation energy. If you do, if you're developing a mechanism, so gas phase chemistry, and you don't know how to start, so you give your molecule, so what do? So you want to show, for example, I place this molecule in, I don't know, 1500 Kelvin. What do you do first? What is the first thing that, you know, when you do these pathways, is that you need to start thinking what the pathways are, right? And so one way to start approaching this problem is maybe bond dissociation energy. So what this tells you is that if I am a carbon and this is another carbon and we have a double bond, or if there is a single bond, what is easier to break, a single bond or a double bond? And so from that kind of energy, you can start building your pathways. Say maybe the likelihood to break a single bond is higher in this case, with these conditions. And then you start the pathway like this. So the dissociation energy and this is a diatomic molecules and electronic energy of this molecule are related. So what you see here is that this is the distance, right, between those two molecules. Of course there is, if they get pushed too much close to each other, so Re, this is the equilibrium, this bond, but then if you push them, they will repel each other. And then if you go this way, eventually you break the molecules, right? And so this is what they call the bond dissociation energy. That is equal to dissociation energy plus this h nu over 2. Okay, so sometimes you do quantum calculations, or you look at some bond energy and you say, I have this molecule, this is the energy that I need to break this bond. It is a D. And so I think this is, I just want to bring you an example. So let's say that you are given to study one of those compounds, okay? It doesn't matter which one it is. Actually, let's do this, is closer to my height here. And so which one is, how do you start? This is a good way to start. Start looking at the bond dissociation energy. So you see here, for example, this is indene, right? So there is a 6-member rings and there is a 5-member rings. Now, if I break this bond, is 80.3. If I break this carbon hydrogen, is 79. This is 85. So do you see the difference? This bond is next to a double bond also, and then next to a single bond. This one, that should be similar, instead is only, this is a single bond, this is a single bond. So those energies give you an initial insight on how to approach this mechanism development and the pathways. And again, it's not like a straightforward carbon-carbon, but the environment plays a role, as you can see here, between 80 and 85, okay? Now, this carbon hydrogen here is 114. The same carbon hydrogen is 79. So you are breaking the same type of bond, but in reality, the environment, so this is double bond here, creates some additional complication. But again, if you want to start somehow, actually, this is a way I started when I was looking at naphthalene. I was very interested in the beginning, 20 years ago, many years ago, and you know, carbon and hydrogen and the chemistry. So how much energy does it take for an hydrogen to come in, break this bond and take away the hydrogen, for example? And so you want to choose, or you want to start from the one that is the least energy here, that is more likely to lose hydrogen. So the one in position 1 or 2 are different. Okay. So what happens if you have a polyatomic molecules? Well, a lot of math here, but in reality we do have math here. So this is methane, this is ammonia, and this is water. Yeah, so water. And the more complicated are those structures, the more complicated is this calculation that you have to do. And again, you don't do this by hand, but the software like Gaussian solve those energy state. So they tells you what level states are available for this species in those conditions. You can have a lot of them, and again, you don't need to go into all those details, but the point is that they are way more complicated than that. You increase complexity, and this is when you increase the number of atoms that are here. Same for the vibration. This is the water that has 3 normal modes of vibration. And again, this is the expression, if you're interested in, for those available states. And here I brought the pictures because it's always difficult to describe them. But the point is that if you give energy to this molecule, whether it's water or they can do all those things. And so they are dissipating part of the energy and just doing this kind of movement, okay? So the question is, the molecule has some energy. You provide energy to the molecules, you are igniting, you are going at high temperature. How does the molecule use the energy, first of all? Some of them will do vibration, some of them will do translation, some of them will go to the electrons. Once you go to the electron, you are breaking or making a bond. Okay? But you need to know that part of your energy goes in all those things. And so, total energy, get more math. So what is the total energy that you can describe? In general, you can have a translation, rotation, vibration, and the energy here, okay? And so those are all the equations if you're interested for this expression for the total energy of those molecules. Now, here comes, it's a lot of math, but I want to show you a picture that I think it could be useful. So let's assume that this is some kind of r distance, and then this is energy, okay? So here you have an upper energy level, maybe excited state, so and this is more the ground state over here. So first of all, what you see, the most important things is that this is the electronic energy. So in general, the electronic energy is much bigger than anything that I showed in terms of vibrational, rotational, and translational energy, okay? So electronic is much higher. Then you go down to the vibration. Remember, I showed you the picture. So this is here. This is the energy. But then, if you narrow down in this blue circle here, now you can have also rotation. You remember those numbers and steps that I showed you? Well, those are almost where they are wider at the beginning and then they become shorter. But if you look at the rotational, they are much shorter at the beginning and then wider here. So you are on this level, this one, you can jump in the rotational energy here. And then you can keep narrowing down that instead of the rotational, the smallest one is basically translational energy here, okay? Again, you need the materials with some property. You need to excite the materials, excited states of this material. You need to know how the energy distributes between those levels. And I think this is, maybe the fundamental message, how the energy partition in those motions. So, I want to show you, this is, I couldn't find a good video, so I took some snapshot, but I want to show you that. Here is a gas discharge tube, like that, and it's filled with the hydrogen gas at very low pressure. If you apply a high voltage to the gas, you start seeing you can ionize electrons, so you give energy to those electrons basically, and many of those atoms are generated in the excited state. So if I go back for a second to this one, what you're doing, you're producing so much energy they can jump on this upper level, okay? So you give energy, they go on the excited state. And what happened is that many atoms of hydrogen are in this excited electronic state, and light is emitted by those atoms as they transition from one energy level to another. So you excite this atom, and then they slowly decay, and once they decay, they emit a photon that basically gives you that those colors that you can see. So each transition is quantized, and so if you record this, if we pass the light into the spectrometer, only certain levels are permitted. So what you see, this is a spectrum, not a great image, sorry, that you can see that the hydrogen, once is excited and then it decays, you can see only some of those are allowed. Okay? It's like a quantization of energy. So you don't have a continuous spectrum, but also only discrete. And this is the reason why you have a neon sign. So what happened is a tube of gas in which, for example, you have neon, you can have argon, you can have different colors, but the current produces an excited state, okay, of those electrons. And then over time, what they do, they decay. And when they decay, they emit a photon that basically gives this color to the neon. Okay? And of course, there's continuous current going through because this is plugged into the wall, if you want. But this is the phenomena, is an excited state of the gas and then slowly decay over time and produce this light. Okay, for the one. Silly question. Do you know that there is one compound in the periodic table that was not discovered on Earth?
Helium.
Very good. So take a look at the helium. So we do the same experiment with helium now. Okay, so no hydrogen but helium. And this was for that before. So what happens is that if you repeat the same thing, sorry, with the helium spectrum, now you're seeing more, still not continuous, but you see all those discrete pieces of information. What is the difference? Well, now the helium has 2 electrons. Okay, the hydrogen has 1 electron. So once you have 2, you have also repulsion between those electrons that plays a role. So the spectrum becomes way more complicated for this, but the point is that, remember, there could be a fingerprint that I told you. So if you have a way to compute the spectrum with the quantum chemistry, let's say that you have a spectrum like this, then you can go back and say, okay, my compound was something like that. So they give information about the spectra also, and this is just a comparison between a hydrogen that has 1 electron, and this is the helium that becomes way more complicated with 2 electrons only. And just to give you some acknowledgement, I thought there was a fun fact here, but so in 1868 there was a solar eclipse, and what this is Janssen, anyway, it was a French astronomer, and you notice there were bright lines in the spectrum of the chromosphere, bright yellow lines, that then was a wavelength of 587 nanometers. And October, the same year, Joseph Lockyer, in England, Same things, he set up a powerful spectroscope, basically, and observed the emission spectrum on the head. And then they both named this a yellow line that they could see because they didn't have an idea, with the Greek word of sun, so Helios, and then it became helium. Okay, so it was not discovered on Earth, but rather looking at the sun, and they come up with this. Again, this is interesting because it's the spectrum that give information about the structures. Okay, so they realized there was not something that they had seen before because of the spectrum. Okay. Hopefully so far with me, it's a good things. Okay, so I'm going to give you a few jumps in the here. So the Schrödinger equation that you can write like this, in which you have an Hamiltonian, you have again this psi function, then you have the energy, and then the psi. My point is that there is a lot of contribution here. This is the nuclei, this is the electrons, this is the interaction between electron and nuclei, 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 electron, electrons. Okay? So if, remember, I want to find some information about the allowed energy distribution of the electrons also here, I need to solve this equation. That's impossible, basically. But those terms are the ones that are going to create problems, and so we need to make some approximation for those. So the first one, what I call Born-Oppenheimer approximation. So the main point is that this was a great step because up to that point, that equation was too complicated to be solved. And so some approximation needed to be made. And the core idea here is that the nuclei are much heavier and much slower than the electrons. Okay? And so what that means, remember that you had all those terms here in which you have the nuclei, and the nuclei with the electrons here that create problems. And so this approximation allows you to electronic motion can be solved independently at a fixed nuclear position. Okay? That highly simplifies the system. And so what they have is called the Schrödinger equation was enormously simplified, but also allow us to define potential energy surface. That is, I'm sure, something that you have seen when you look at gas phase mechanism. And then justify the molecular structures with the fixed nuclei, but there were limitations to that because basically it breaks down when electronic and nuclear motions are strongly coupled. Okay? So the point is that let's split them, the behavior, but they are a system in which non-adiabatic process or photochemistry in which you cannot do that. So it's an approximation that works well, for example, in also some cases for combustion, so you have seen those of that. And so more specifically, this H that I was mentioning, the Hamiltonian, that is component. So the first term is electron, the kinetic energy of the electrons. The second is the nuclei, the kinetic energy of the nuclei. This is a Coulomb attraction between electrons and nuclei. Then you have repulsion between electrons and repulsion between nuclei. With the Born-Oppenheimer approximation, what you do, H becomes these electrics, if you want to, H, and then you have, you retain this one, the first one, and you retain this one, that was the electrons and nuclei, and you get rid of this one, okay, go to the nuclei. So easier math, if you want. There is a point in all this, because I needed to take you to transition states, to compute rates and pathways, right? And without this, there is no way we can talk about that. So the electronic Schrödinger equation, basically, or ESC they call, is basically this simplification. This is Max Born and Robert Oppenheimer that did that. And so for us, that was a big step, but again, you are neglecting those nuclei and energy and electron interactions. And then it came the problem with many electrons. What if you have a lot of electrons? So electron-electron repulsions, also in that term in the Hamiltonian, is very complex, okay, to get an exact solution. And so here comes Hartree-Fock method. There was a huge approximation. It basically treats the electrons as moving in a field with all the other electrons, okay? And so going through some of the concept here is that I want to simplify the Schrödinger equation. The electrons influence each other, but the limitation is that they ignore the correlation between the electrons. Okay? But they give you a much better balance. So accuracy versus computational cost. So this is another way. And again, if you read or review some of the papers, because eventually you are going to be a reviewer, or also you're already maybe looking at some of the papers, people describe this new mechanism, or they computed quantum chemistry and they have potential energy. These are things that you have seen many times. Depending on the method that they use, they're making some approximation. And so, as I was mentioning before, situation in which there is a correlation, the Born-Oppenheimer is not going to work. This one is another, R3-FOC is another way to do that. That has also some advantage, again, in computational cost. So R3-FOC method is approximate, is an iterative computational method, and basically helps us to solve this expression for the Schrödinger equation. So briefly, what are the core approximations when you talk about R3-FOCs? First of all, there is a Born-Oppenheimer approximation. So nuclei are considered fixed because they have larger masses. The complex, when you have a multi-electrons, I show you with the helium, if I have 2 electrons, it's already more messy. When if you have multi-electrons, wave function is approximated in this case as a product that's called the Slater determinant of electron wave function. And so instead of calculating the repulsion between every pair of electrons, remember there is a term in the Schrödinger equation, the Hamiltonian, each electron is treated as a moving in an average field. So I'm making some of those approximation here too. And the last things in this story is that usually when you look at those papers, they solve it with some basis set, okay? So what you're doing are basically looking at the molecular orbitals that are some mathematical form that describe the probability of an electron in a molecule. Remember, electrons get together, they can make a bond. So you want to know where are located those electrons somehow. So that's the reason why we are solving this. And so another approximation that they do when they solve this equation is a linear combination in which you have those molecular orbitals function of those basis set that you can look at. And then basically you solve this equation and you optimize this parameter C. Okay? Again, there are more details here that maybe what you want at this point, but if you ever want to go back and look at some of the keywords, just see what method relates to what and what are some of the limitations I want to show you. So the last thing for this R3-FOC is that what he does, the electronic wave function, so as I show you, is just a product. They do this determinant, okay? And then varying the molecular orbitals until the electronic energy is minimized. So what it does is basically the method optimizes the shape and the energy of these molecular orbitals until they calculate the electronic energy. So if I go back here, basically what you're doing here is optimizing this C in this reaction, okay? What are the limitations of R3-FOCs? We talked about Born-Oppenheimer. Let's look at this one now. So it neglects the dynamic electron correlation. So the primary weakness is that it doesn't account for correlation between electrons, especially when you have different spin. And so you overestimate the energy of the system. Computational cost, calculation of 2 electrons integrals is demanding, and they scale as n to the 4th, where n is the number of the basis functions, okay? So an idea to give you some tools when people say, I studied this reaction and I use this basis set or this approximation, you have a feeling of what kind of things they were neglected, and therefore you can assess if the system is well represented with these things. Okay, last one, and again, I brought you some more information that maybe you want at this point. You can always go back and see. This is very famous, so you will always hear a B3 lip, but now you have an idea that maybe is related to DFT if you want. So one more approximation. People were trying many ways to solve the Schrödinger equation. There were 2 different theorems that are contributed. So Hohenberg-Kohn theorems and the Kohn-Sham equations. So this tells you the first one, the ground state is a function of the electron density. And in the second one is that they reformulate these multi-electron problems into a single electron problems. So remember that we are talking about multi-electrons with R3-FOC. Well, they created this exchange correlation function to solve this problem. So some of the experimentation here is, again, B3, MO6, they are widely used right now. So the first theorem is the ground state energy that on many electrons is a function of the electron density, okay? So this density is a much easier to handle if you look at the Schrödinger equation than the wave function. The second part is that for a given potential, the ground state density minimizes the energy of the functional. And so we can find the true ground state by searching all the electron density, okay, of the system. So this is important for this calculation. And I'm going to I'll give you a quick highlight of this equation. This is the V sub xc is basically this exchange component that they introduced. And this guy is unknown. The choice is critical, and you need to choose that to start those quantum chemistry calculations. Okay. Advantage. I want you to know anything about this DFT. Okay, so DFT is great if you have to start looking at some gas phase chemistry. And again, one way to start is the bond dissociation energy. Which one is the easiest? Then I will start thinking about what are the pathways, how can you break bond? And then you choose. Maybe DFT is, I think, the most used method right now. Advantages is accuracy to cost ratio is great. And requires usually, I mean, the accuracy could be compared with some of the R3-FOC method. It includes electron correlation, so that is important, and is scalable, so that especially when you have larger system, okay, and to the 3 or to the 4 component. The disadvantage that you have here is that the accuracy relies on the Vxc that I just showed you, the exchange correlation function, and there is no universal best function. So when you think about this and choose, that is something to keep in mind. And then may struggle with some interaction. This was a cool thing. Dispersion forces, okay? So with new functionals, and they are addressed with new functionals. Okay, one of the PhD students, I was on the committee and I made a mistake. I was very young and I said, you're doing DFT, but there are no dispersion forces, you know, for the simulation. And so they didn't like my question. So, but you need to know that if you're doing a DFT simulation, especially older ages, there were no dispersion forces between the atoms, so you are neglecting some of the contribution. So, few keywords for you to keep in mind and decide what you want to use. Okay. So, now we have energy. Somehow we have the energy of the molecules. We have some idea on how they are distributed. So now we can look at potential energy that I was showing you, right? We approximated the Schrödinger equation with the electrical Schrödinger equation. And so once we do that, the landscape, you can look at the landscape of energy versus the molecular geometry, okay? So I have reactants, I have a product. The next step is to add the transition state also. So the transition state is basically the highest energy point along a reaction pathway. And then there is an activation energy, that is the energy required to reach the transition state. The reaction coordinate, so it is the path connecting reactant to products through the transition state. And then when we want to talk about kinetics or thermodynamics, you still use this, but kinetics, we are going to talk about rates. Thermodynamics are going to use stability, so you will see the energy difference between the molecules. Okay. So let me give you a brief summary, and then we'll take a few more minutes to break, and then we can go directly into the combustion part. So quantum mechanics, and I know I gave you a glimpse, but maybe there are some information that you want to retain or look up in the future. So quantum mechanics, it's important for the electron behavior and the molecular energy that I need. okay? From quantized energy to vibration and the Born-Oppenheimer approximation, you have some tools to describe the molecules. Okay? You know what kind of energy level they are allowed. Okay? They can store energy. DFT and transition state can help you with predict some reaction pathways. And then let's see how they apply to combustion. And I want to start with a little bit of summary, because I'm sure you wonder why we did all this DFT or whatever, because I do need DFT information to really jump into the transition state, okay? So maybe you want to take a 5 minutes break, and then we'll do the rest part of this section for this morning.